Thank you. Good morning. So yes, I'm going to start the day, and I want to share with you a couple of things. I want to share why I think that Agile brings in a new paradigm in software, and also why I believe that DevOps is really the important game changer that enables this revolution to happen in the first place. So, the idea for this talk actually came from this book, The Structure of Scientific Revolutions. It has a fantastic pattern, and that's really what I want to share to you today. DevOps, Agile software, that's all fine, and it's really interesting. But the pattern that is described in this book, once you've learned it, you'll see it over and over again, and that's why I saw it in the software industry. So, this book was written by Kuhn in the late 60s, and it was really a groundbreaking book. What he did was, he was a PhD in physics, but he was teaching a class in the history of science, actually, how science evolved over time, how we've learned over time. And what he found was very interesting in the sense that up until this point, everyone thought that progress in science had been made in an incremental way. But what he found is that actually, that's not true at all. Generally, things go along in some kind of normal paradigm until there's a big revolution and everything is upset and the whole industry has to start again, or the whole field has to start again. Sorry, excuse me. So this is the general idea of how science works. This is the scientific method. This is what we're taught in school. It's the Popper method. And the idea is that science is about making observations, forming hypotheses, trying to test them in some way, gather data on those tests, and verify whether your hypothesis or your world view, the model that you have of the world, is correct. And this is the hamster wheel of science. We just go through this over and over again. But that's only a very, very small part of the story. And that is not the most important way that we make progress in science. What really drives forward any field in science is these acts of revolution that occur over and over again. So Kuhn, in his book, describes this cycle in which science goes through over and over again. And this is the model, this is the pattern I want to share with you today. So normal science is kind of like the Popper method that we saw earlier. And it's all about science happening within a paradigm, within a worldview. Everyone shares this worldview in the field. The basis of the field is understood. There are textbooks, there's an agreement, a general agreement about the way things are. And science, during this phase of progress, is all about bringing nature and science into closer agreement, just refining and refining and refining. And the important thing is that basically scientists take the field, or the basis of the field, the foundation, for granted. They don't argue over the things that are in the textbooks. So some good examples of this in modern times that are both incremental but also very famous are the Large Hadron Collider and Dolly the Sheep. They're incremental, not in the sense that they weren't big, huge undertakings, but they more or less get the results they expected. The Large Hadron Collider went seeking the Higgs boson, and they found the Higgs boson. There wasn't a surprise there. When they cloned Dolly the sheep, they expected to get a clone of Dolly the sheep, so they got exactly what they asked for. The thing is, though, after a while, when you're in a paradigm, unresolved anomalies start to accumulate, things that don't fit and can't fit in the basis of fundamentals of the field. So some scientists start to question the paradigm itself. The important thing is, even if things don't quite fit in the paradigm, people will still hold on to the paradigm and believe in it and work within that paradigm because there's nothing else, there's nothing to replace it. We all need a paradigm in which to do our work. So unless there's a better paradigm on the table, we'll stick with what we've got. After a while, these anomalies can accumulate to the point of crisis where there's so many anomalies that everybody in the field is starting to argue. It's all-out war. And then starting to question the fundamentals. The textbooks are ripped up. Everything is on the table again. Now, the only way to get out of a crisis is with a new theory. And this is where we get the revolution. The revolution gives us a new theory for the fundamentals of our field. And if it is the winning paradigm, it will replace the old paradigm. And we get our paradigm change. And when this paradigm change has happened, older views, people that hold on to the previous paradigm, are basically written out of the field. Their work is ignored. They are no longer relevant. And it kind of follows the Harlan pattern. There can only exist one paradigm at a time in a field. If there is more than one competing paradigm, then you're still in a crisis. You're just in denial. So there we are. So science is all about working in paradigms and then having revolutions. Paradigms, revolutions. And this is the normal way science develops. This is not a flaw. This is not a bug in the system. This is how we make progress. So some examples. I mean, for most of history, we thought we were the center of the universe. Some people still believe that. But it made sense, right? We're standing here and everything is going past us. You know, the sun goes past us, the moon goes past us, the stars go past us, so it makes sense. But over time, the anomalies started to creep up. And Copernicus was looking through his telescope and saying, wow, what if instead of us being in the middle, what about if the sun was in the middle? So we had this shift from geocentrism to heliocentrism. And in Kepler, he was making lots and lots of data gathering, creating all these tables to understand the movements of the celestial bodies. So between the two of them, they had both the theory and the data to be able to form this new paradigm. We're going to completely change our worldview. And after it was accepted, anyone that still believed that the Earth was the center of the universe were just irrelevant, right? And the next big paradigm shift that happened in physics was with Isaac Newton, with his fundamental laws of physics. And what he managed to do is to say, well, what about, at least up until this point in history, there was this belief that the way things happened out in the stars, in the sky, the celestial world was different from the world on Earth. It had different rules. But what he said is, well, what about if there's some universal laws that apply to both the stars and the moon and the sun and the Earth that apply here? What about if the way a cannonball moves is the same way as a planet? And, you know, we get the universal law of gravity and so on. And Newtonian physics lasted a really long time. But eventually the anomalies started to creep up. I mean, Newton had a lot of really great ideas, but he really believed in fixed space and time. And then, you know, we learned a lot through electromagnetism and Maxwell's equations. Things were starting to come apart. And then Einstein is saying, well, what about if space and time can be bent a little bit? And it's actually the speed of light that's the constant in our universe. And on it goes. This is just the normal way that we progress in the field. So how does that apply to software? I think we don't have as long a history, but we can see a lot of the same patterns in the way that we've had in our industry. So I argue that the start of the field for software was Turing. You can go back to Lovelace and Babbage and further on, but I think that general purpose computing was really the start of the software industry, and it starts with Turing in the late 30s. And it wasn't that long until we got our first crisis. In fact, it was called the software crisis in the late 60s. And Dijkstra mentions, he says that, okay, when we started, computers were really simple. So programming was easy. Then they got a little bigger, and it got harder. And now the computers are gigantic. And now we're having a gigantic problem. It was called the software crisis. And this is a quote from the 1968 Software Engineering Conference. And the name of the conference gives you a clue to how they believed the best way to get out of this crisis. It was with engineering. So he said, what about if we start to apply the principles of engineering to software? Wouldn't that help us? Wouldn't that be the the way out of dealing with this complexity. People who build bridges are dealing with a lot of complexity as well. Maybe it's the same thing. So we started to go down this route. We had structure, systems analysis and design, SSADM. We had structured programming, data hiding, object-oriented programming, requirements analysis. It was all about like making a plan and working the plan, because this works in other fields. We found a way out of this crisis, and it worked phenomenally well. We had decades of amazing progress in our field using this model. The thing is, anomalies started to creep in over time. We were seeing that there was a lot of big software projects following good engineering disciplines that were still failing. This is a fantastic Wikipedia page. It's about software failures. It's my second favorite Wikipedia page. And if you ever have 5 minutes with a cup of coffee and you just want to have a giggle, go and have a look at this page, because it's got just a list of all the giant failures in our industry. And some of them are huge. Some of them are actually close to my home. We have this, the NHS for Connecting Health project, which was £12 billion, around 120 billion kroner. That's a lot of money. That's taxpayers' money. That's money we gave to the government. And none of it went into production. None of it. So we started to have these failures. And it was, even if we were using CMMI level 5 consultancies, even if we were doing all the planning up front, even if we spent a lot of time making sure we had the right things, we were still failing. And so something wasn't right. Maybe engineering wasn't going to work. We had different kinds of anomalies too. We started to see other large projects showing incredible success, not following any of these engineering principles, like GNU, Linux. The list is endless, but there was a lot of, at least in the early days, a lot of open source coming through that were showing that actually it doesn't seem to be as important as we thought to be following project management principles, structured analysis, doing requirements. All these things didn't seem as important in the end. And we started to see, okay, maybe there's something wrong with our paradigm. Maybe we're not in this engineering thing after all. So we get into this crisis. What if we're not actually building bridges? What if instead we're trying to optimize the production of a car? What about if software was more like manufacturing cars than building bridges? It's kind of a hard thing to take. It's much, much less prestigious to think about yourself working in a car plant, right? But it turns out there's a lot of things in Lean that were super applicable to where we are. And during this crisis, there was a lot of people arguing. And nobody argued more than the people who signed this document. They argued for years and years about the best way to make software. And they had a lot of things that they didn't agree upon. But they did manage to agree on some things. And that's where we get the Agile Manifesto from. They did understand that, okay, maybe there is some common thread to all the things that we see that makes sense in all situations. And that's where we got the Agile Software Manifesto. And a little bit later, we got some principles to go along with it. And the very first principle was, the highest priority is to satisfy the customer through early and continuous delivery of valuable software. That's great. So we have Agile, we have this idea of continuous delivery, satisfying the customer early, all the time. Let's be like Lean. Let's turn our software organizations into Toyota. Great idea, but nobody knew how to do it. It was just a theory. And to resolve a crisis, to get a revolution, a theory isn't enough. You also need achievements, and those achievements have to be unprecedented. Has to be something that would never have been possible in the old paradigm, and they also have to be open-ended. Basically, with this sparking a new revolution, what you need to do is attract a lot of talent to this new theory. And the best way to do that is to have lots of problems. Like, as scientists, engineers, technicians, we want to solve problems. The most important way to get anyone interested in what you're doing is not to come with a solution, but to come with a problem. Then everybody gets involved. So I would argue that it was a while before we got these big, unprecedented achievements. But they did come. I mean, we had Google, we had Facebook, we had Flickr, we had all kinds of companies showing incredible velocity. And this presentation at Velocity 2009, about 10 deploys per day for Flickr, was seen as really groundbreaking in our field. And then we started to see, okay, maybe there is something that is common to how we get this agile continuous delivery. Maybe we have a thing called DevOps. And then we started to have lots of people attracted around all of this, all of these interesting open-ended problems. So there we get the spark. So an interesting thing about revolutions is that there's a correlation with revolutions and tools, and in science at least. And remember, this was written in the 60s, so it was very prescient as well. And what Kuhn is saying is that if you're getting a revolution, basically everything has to get thrown out and started again. You're going to get new theories, but you're also going to have a lot of new tools in this new paradigm, and you're going to have new textbooks. Everything's going to change. So it's also an opportunity to retool. And that is also true in software. I mean, we've seen this continuous delivery DevOps thing be the driving force to making us retool our organizations. And if we wanted to go back in history, we can see the telescope made possible the Rudolphine tablets, the fact that we could start to gather really good data about the planets. And without that data, Isaac Newton wouldn't have been able to prove his universal laws. It's the same thing with the stethoscope. There was a time, for most of human history, that the way you could find out how someone died was to cut them open and have a look. So there wasn't a lot about looking inside the body to find out why people were sick. But René Laennec understood that, well, maybe if I can invent this thing called a telescope and start listening to people as they're dying and finding what sounds they made, and making good analysis of that data, publishing that, then we can start to understand. So, rather than cutting people open, we can know what's wrong with them before they die. So this is like the start of non-invasive diagnosis. You could take it even further. Maybe this is stretching the analogy, but without compass navigation and shipbuilding, we wouldn't have had the Beagle expedition, where Darwin collected all the sketches and data to back up his theory of evolution. Sometimes it goes a different way. Sometimes it doesn't go tools, data, theory. Sometimes it goes theory, tools, data. And that was the case with the Higgs boson. I mean, the Higgs mechanism was first postulated in '64, but it was 50 years later before we started with the Large Hadron Collider, and it took us a while to actually gather all the data to really find that we have a Higgs boson. So it's not that they have to come in that order, but you need all three to make it work. So you need tools and data plus a theory. So we've got this theory that Agile can improve business outcomes, but do we have the tools? Do we have the data? At least until recently, I would say the answer to that was no. We had a gut instinct. We felt Agile was the right thing. And we all did Scrum classes. And we all, changed the way we thought about our working processes. But we didn't really have the tools and data to back it up. And that's where I argue that we're kind of getting into the normal science. We're starting to do the tool development and the data gathering to actually spark this thing. So you can think of, there's a lot of things going on in this diagram, but the important thing to understand is that imagine that this is your software organization, your technology organization. It exists for one reason, and that's to take a request, a need, a business need of some description, and deliver it. That's the only reason why your organization exists. So the only thing that matters is really how long does it take to meet the needs. That's the only measure of success. This is the only metric to improve. We had a discussion yesterday about metrics and how they should be business driven. I would argue that one of the things you want to look at is how effective you are. What is your lead time to meeting the business needs? And you can do a lot of automation to make this happen, or at least for lots of this. And in order to get that automation, we need a lot of tools. The nice thing about tools is that not only do we adopt them, but they adopt us in a sense. They change the way we work. Just a show of hands, how many people are using more than one of these technologies on this slide? Okay, that's everybody. And all these tools were created within the last 10 years, basically since DevOps was a thing. And we're really fast at building and adopting new tools. That's the great thing about our industry, and that's why we're able to have such progression in our field. That's why it's moving so fast. So that's it. We want to turn as much as possible of our process into code, because that's the way we reduce the lead times. Just like in a factory floor, you look at optimizing the flow. So we want to have our configurations as code, our infrastructure as code, our test as code. Whatever we can automate, we want to automate. And also, we want to make sure that we're all as one team. We want to make sure that everybody is in the same team. The testers, the business, the security, the developers, everybody's in the same team, optimizing just for this flow. So I kind of feel like we're past the revolution now. I think that the revolution really did start 10 years ago. The theory came in 2001, but I think it was like 7 or 8 years before we had the revolution, when we started to get the achievements from it. So now we have to get into the data gathering. We have the tools. How do we actually prove any of this stuff? There's been a lot of work in this, and one of the leaders in this is the DevOps Research and Assessment Group. They're based in America, but they do surveys of IT organizations across the whole world, across all different industry types, and they ask questions about the way organizations are making their software. And the important thing is that they do it in a scientific way. They ask statistically significant questions. And a lot of their findings are actually published in peer-reviewed journals. They also have this State of DevOps report that they publish once a year, and it's free. I think you just have to give your email. And it's got a trove of information. There was a discussion yesterday about how to convince your managers or your teams about DevOps. This is a really great way to do this, because there's a lot of fact in here. It's not theory. There's a lot of fact in this report. So there's a lot of numbers as well. So if you want to dig into it, you can see lots of numbers that show that DevOps can actually help, and that's important. But for me, what the real strength of this report is it shows you the cause and effects. What actually drives performance? There's a lot going on in this, so I just simplified it a bit. But the most important thing to think about is financial outcomes. What are the financial outcomes for the business? What drives better financial outcomes for the business? And what they found was that two of the main drivers are lean principles, lean product principles, and continuous delivery practices. So for continuous delivery, you need a lot of practices and tools, trunk-based development, test automation, and so on. And none of this works. You can't have lean, you can't have continuous delivery without transformational leadership. So it all starts with the leadership. You don't get anywhere without the leadership, but all of these aspects play a part in getting those financial outcomes. But the important thing is they can establish a cause and effect between high performers in DevOps and those that have good financial outcomes. Now that's fine and well for the industry, but what about for your organization? Well, one of the things I'd argue is that you can take a similar kind of approach to data gathering in your own organization and start to measure the things that are important to you. Like I said before, I think the most important measurement you can have is how long you take to satisfy a business need. And that's your basically the lead time for your software organization. You can dig more into development lead times, build lead times, pipeline lead times, release lead times, all kinds of things. And a lot of this is really easy to get. You can get it from your task tracking systems, you can get it from your CI systems. It's all there. You have the data already. You just need to go and dig for it. So it doesn't have to be a big project to figure these numbers out, but it can give you important feedback on how you're doing. The best place to start, of course, is with the one team and getting everybody involved to see the full value stream for your organization. Because this is something that we're not very good at as developers or development teams, is including the business, including the operations, including the security. We're quite happy at sub-optimizing in our teams. We do our retrospectives in our teams. We plan in our teams. We refactor in our teams. But we don't really think about the whole value stream so often. So just getting everybody in a room and mapping out the full value stream can have a huge impact. Okay, so how does that leave us then? We're in the boring part now. We just have to do the work. We have our new theory. We have gone through the revolution. We've got the tools. We need to gather some data, but mostly it's a bit of a yawn, right? Well, there's a bit more to it than that. Andy Grove has many, many good books. He was the CEO of Intel, and he took Intel from being primarily in the memory business to being primarily in the CPU business. He has many, many good books. I recommend all he's writing, but this one is especially good because in it he talks about that transition from turning Intel from being a memory company to being a CPU company and all the challenges that had. I think we're seeing a very similar thing right now. You see more and more companies talking about digital transformation, talking about DevOps, talking about cloud adoption, all these things. But I think that there is going to be winners and losers. Andy Grove knew that if he stayed in the memory business, he wasn't going to have a business in 10 years because the prices were going down, the competition was going up, and frankly, the competition was much better at making memory than Intel was. But changing that organization, changing the whole structure, took an incredible amount of work. So the important thing is that the future is here. People are already doing a lot of this stuff. We don't have to invent all these things. Most of the problems have been solved somewhere. It's just to dig around and find out what's working for people. And obviously, conferences like this help a lot. For sure, you don't want to be the first to adopt technology in this space because everything new is broken. It's just a universal fact. All new technology is broken, but a lot of new technology has value. So you can for sure play with it, but you want to wait until it's mature enough that you can actually use it with success, but not. Definitely don't want to be the last to adopt new technology either. The important thing now is that because tools are changing so often, you want to really think, how do I optimize for replacing the tools that I have? How do I optimize for replacing the way I do things? So that's the thing to optimize for. And yes, learn from the community. Come to events like this and contribute. So that's it. That's my argument. I believe that DevOps kind of really defined the paradigm that we're in right now in software. I think that nobody is going back to the old approaches of software development. I think there's no going back. There's only going forward from here. I think that Agile was the theory that sparked all this. Agile was really important. It just wasn't enough. It didn't say how. It was what we'd like, but it didn't say how to get there. And that's what DevOps does. And we're kind of in the boring bit now. We just have to get on with it, build the tools, gather the data, incrementally make progress. And I think that this is, and there'll be winners and losers in this process going forward, I'm sure of that. Good. So thanks for your attention. Hope you enjoy the rest of the conference. If you want to talk more about this, I'd love to. Grab a coffee. Yeah.
Time for a few questions by pure magic.
By pure magic. Are there any questions?